All right, good morning, you guys. Today we're looking at statistics and we're focusing on geometric distributions. So first up, a geometric distribution is a type of discrete probability distribution of a random variable x that satisfies the following conditions. So like the binomial distribution, each observation or trial has two categories, success or failure. Like the binomial distribution, all observations are independent, so we know that one outcome does not influence another. Like the binomial distribution, the probability of success, P, is the same for each trial, but where they differ, this is the big one, for geometric, trials are repeated until we achieve a success. And sometimes it's really until a failure occurs. So I could flip that around as well and write in, well, sometimes it's until failure occurs. Okay, so our formula is pretty user-friendly. The probability that the first success will occur on trial number X is going to be, here the P is the probability of success. Okay, the Q is the probability of failure. And then it's raised to, really, the count of failures, the number of failures. So before I move forward, let's imagine that we are rolling a die. Okay, so rolling a die and say looking at getting a 4. So I know that I have a 1 in 6 chance of that scenario playing out. Let's say that I'm looking for, what's the likelihood that I rolled a 4 on the 8th try? So if it takes until my 8th try, that means that I've had 7 failures preceding that success. So that means I would have had 7 failures, and then on that 8th try, I got to my success. So for the formula, I would have 1/6 times 5/6, that's my probability of failure, raised to the number of failures. I would have had 7 failures because I achieved my success on the 8th try. Okay, that's the type of geometric probability question that we're going to be able to solve. All right, finding mean and standard deviation. So again, here I will always give you these formulas. Okay, I will provide them to you by the time that we take a quiz. I don't need you to memorize them. So our mean is always going to be 1 divided by P, right? That's our probability of success. And our standard deviation will be the square root of Q divided by P squared. So Q is our probability of failure. P is, again, our probability of success. So the differences between geometric and binomial distributions, right? I'm not going to mix them up today for the calculation problems, but I will soon. So here, just to make sure that we can tell the difference first and foremost. So the most obvious difference is that the geometric distribution does not have a fixed number of trials, n. Binomial distributions, we always have that. We're rolling a die 10 times. We are flipping a coin 6 times, etc. Right? That's binomial when you have a fixed number of trials. The second most obvious difference is just the question that's being posed. So for binomial, we're asking for the probability of a certain number of successes. So I'm looking for, 4 heads out of 10 coin flips. That's a binomial question. For geometric, it's asking for the probability of the first success. So for geometric, you have a series of failures until you finally obtain that success on the last trial. So for geometric, again, we do not have a fixed number of trials. And for geometric, we're looking for, when does that first success occur? What is the probability of that outcome? All right, so in example 1, I'm really first just looking at which is which. Is it binomial? Is it geometric? So first up, we got Carla. She makes random guesses on a 25-question multiple choice test with 5 choices per question. we want to know how many questions Carla guesses until she gets one correct. So this to me, right now, I can say, well, that reads as geometric to me. So it's geometric, and then, well, why? Why is it geometric? Well, we have no fixed number of trials. And we also know that Carla really just keeps going until she gets to that desired outcome. So Carla keeps guessing until she gets to that desired outcome. So until she achieves her success, answering a correct answer. Okay, for 2, we want to know the probability that she answers exactly 20 questions correctly. So we're saying, well, there's a 25 question multiple choice test. What is the likelihood that she gets exactly 20 questions correctly? Well, that's binomial. So here this would be binomial. We have the fixed number of trials, right? We've got that 25 question multiple choice test, and we're looking to calculate the likelihood that she guesses 20 questions correctly out of those 25 total questions, right? So that triggers for us, got to be binomial. For situation B, in an attempt to increase sales, a cereal company decides to offer a promotion. 20% of cereal boxes will contain a collectible card featuring NBA superstar Steph Curry. Okay, what is the probability that an NBA fan gets 3 collectible cards after purchasing 10 boxes of cereal? So here we can say, well, that reads as binomial. The biggest identifier is, again, that we have a fixed number of trials. Right? She's purchasing 10 boxes of cereal, and we're looking for what's the likelihood of getting 3 of these collector cards, Steph Curry, out of the 10 cereal boxes that are being purchased. Okay, for 2, what is the probability that an NBA fan gets the collectible card on her 6th cereal purchase? Well, this is geometric. Here we have no fixed number of trials. Right? We know that our NBA fan really has a series of failures until that success is achieved on the 6th purchase. So here again, series of failures until we achieve a success on that 6th purchase. All right, flip it over or go to that second sheet, please. Let me get situated. Okay, and here we just have one big problem. All right, so here, according to the Pew Research Center, the response rate for telephone calls or telephone polls has cratered over the past 3 decades. In 1997, the response rate stood at 36%, but as technology like wireless phones, caller ID, and telemarketing proliferated, response rates fell dramatically. By 2012, Pew's response rate stood at just 9%, where it held throughout 2016. Pew's data suggests that decline is underway again, with response rates slipping to 7% in 2017 and 6% in 2018. Using the 2018 response rate of 6%, find the probability that a pollster gets his first response on the first call. Okay, so first I'm just going to lay out what is my probability of success. So 0.06, right? That's that response rate of 6%. So failure, the Q, would be the complement of success, so 0.94. So here we're saying, well, success on the first trial, instantly successful, X is 1. Well, I already know it's going to be 0.06. But if I follow my formula, well, I can say, well, that would be 0.06 times 0.94 to the 0 power. Okay, and that really confirms for me that it's just going to be 0.06. I have 0 failures that precede that success, and anything to the 0 power would just be 1. So again, just confirms if we are immediately successful, that probability is 0.06. Okay, if we're successful on the second call, x is 2 this time, we would say 0.06 times 0.94 to the first power. So if we're successful on that second phone call, that means that we had 1 failure before we got to that success on the second call. So I just have to multiply 0.06 times 0.94 in my calculator, and I end up with 0.0564. Okay, successful on the third call. So x is 3. So here I'd have 0.06 times 0.94 to the second power. So again, if I'm successful on the third call, that means I had 2 failures before we get to that success on the third call. So here, let me just show you how we plug that in, just to make sure we're all on the same page. So here I'm saying 0.06 times 0.94 raised to the second power, just like that. So I end up with about 0.053. Right, I keep having you guys round to 4 decimal spots. So here it just worked out to be 0.053. Okay, successful on the fourth call. So x equals 4. So 0.06 times 0.94 to the third power. Okay, that will get me about 0.0498. Okay, successful on the fifth call, right? X is 5. So 0.06 times 0.94 to the fourth power. So again, I have 4 failures that preceded that success on the fifth try. So here this will get me about 0.0468 right there. All right, next in F, I'm saying, well, what about on the fourth or the fifth call? So that means that X could be 4 or 5. Well, that's easy enough. I just have to add those 2 up. So the probability of being successful on the fourth try was 0.0498, and being successful on the fifth try, 0.0468. So here we have to add these up. So when I do so, when I add those up, I get to about 0.0966. Let me slide that up just a little bit to here. All right, before the fourth call, so before the fourth call means we could have been successful on the first try, the second try, or the third try. So here I need to go back. I've already solved for these, but I need the probability that we were successful on the first call, second, and third call, and then I have to add those up. So first call was the 0.06 at the top of the page. Second is 0.0564, and third, 0.053. So again, I just got to add these up, and after I crunch that, I should get about 0.1694. Okay, after the fourth call, so that means it could have happened on the fifth call, the sixth call, the seventh, or so on, right? It just has to be after the fourth call. So there's no fixed end point here, right? Because it could take forever to get to the success, to get someone on the phone to participate in our political poll. So here we have to go through the complement. So I need to do 1 minus the probability that we were successful first, second, third, or fourth. And we've already solved for all of those. So 1 minus, I've already calculated the 1 through 3 right here. So here's 0.1694. And I've already calculated the exactly 4 also. That was a 0.0498. So once I get those together, I'm really doing 1 minus 0.2192, and that's going to get me about 0.7808. All right, and then the last question, right, if the pollster keeps calling until he gets a response, how long do you expect it to take and with what standard deviation? So it's asking for, first, what's the mean? And it's geometric, so 1 divided by p. So here I'm looking at 1 divided by 0.06, and I get about 16.6667, like that. So that's telling us how many calls we expect to make on average to be able to get a response. Okay, with what standard deviation? So again, this is our indication of variability, how spread out our data is in relation to the mean. So I'm looking at the square root of q divided by p squared. So when I plug it in, square root 0.94 divided by 0.06 squared. Okay, let me show you how I type that in. So I usually start with the 0.94, and then I'm dividing it by the package of 0.06 squared. So if I type it in like this, that's what's going under the square root, and then I square root that answer. So I'm getting about 16.1589. So standard deviation is about 16.1589. So again, if I summarize that, that means that we would expect it to take a political pollster an average of 16.6667 calls to get a response, with a standard deviation of 16.1589 calls. All right, we should be good with our intro to geometric distributions and probabilities. Have a wonderful rest of your day.